So this is my research, leveraging large language models for code mix data augmentation in sentiment analysis. Right, so I just want to start off with a show of hands. How many of you are familiar with a little bit of Spanish? Well, and how many of you know the meaning of cornflakes? Any guesses? So actually, cornflakes refers to any cereal, and it comes from Spanish English, which is when Spanish-speaking people see cornflakes, they started using cornflakes to refer to it. And this is in Spanish or English, it's a mix of both. Right, so this is an example of code mixing. And code mixing is just any time when two or more languages are being switched between each other in a single sentence. And this is incredibly common all around different societies all around the globe. And this is widely prevalent, and we can see this even in the WOVA app. There's conversations going on in both Vietnamese and English mixing together at this conference right now. And so in general, code mixing has a huge impact for spreading information, for reflecting social pressures, for business product analysis, and in general, it's an important task for diversifying AI assistance. The issue is that many multilingual NLP approaches fall short in code mixing due to data scarcity. This is because it's a very common and casual occurrence instead of documented. Especially large language models, they do not have a consistent performance. And so we aim to augment the amount of code mix data out there in order to improve performance. And so our central question was, are large language models capable of generating natural sounding code mixing? And these code mixing data points that are generated would then be used to improve sentiment analysis or emotion recognition performance. Right, so what we do is we first take a few natural examples of code mixing. An example would be like, con fleas con plátano, narconovelas, what could be better after a long day? And this is just a Spanish Twitter tweet. And then it's been labeled. And we feed this along with a prompt into GPT-4 and ask GPT-4 to generate more similar examples like this. Once we generate these similar examples, both the synthetic and natural samples are used to train a sentiment classification model, which is just transformer-based. And through this, we want to see if the synthetic data helps improve performance compared to just natural data. So we test this on both Spanglish and Malayalam-English, which is a more low-resource language pair. And essentially, from only 15 natural examples, we can get to 50,000 generated samples, all from GPT-4. Right, so we actually find that these generated samples improve performance by upwards of 10%. So from our initial baseline, which is just natural sentences, adding synthetic data increases results in Spanglish to 0.603 in F1, and this achieves third place on the dataset benchmark on Lynchy. And yeah, on Malayalam-English, the results are slightly different. The initial baseline is very high, and as a result, synthetic data does not significantly improve on results. So we do a few more experiments on different models, different data settings, and we find the general trend is when you have low baselines, they lead to higher percent improvements. And this makes sense intuitively because there's more room for synthetic data to improve on performance. And so this also means that when you have a situation that's very resource constrained, you have very little natural data, synthetic data will help a lot because it'll help increase the amount of performance despite a low baseline. Yeah, we can see this here. All right, so we've established that the synthetic data can help performance, but does this imply that it's natural sounding? Well, we ask human evaluators to evaluate code mixing sentences, both human and LLM generated, for their naturalness, their label accuracy, and predicting if they're human or LLM generated. And we find human annotators cannot find significant difference between these two groups. Furthermore, we also compare this toward a technique where you take an English sentence and you randomly translate parts of it into a different language. And these sentences are actually much worse in improving performance than LLM-generated sentences, meaning LLM-generated sentences are more intentional than, say, randomly translated ones. And ultimately, we find that natural soundingness is a subjective measure, but these all hint at LLMs being able to generate sentences that at least can help model performance by giving more good code switching examples. Right, so some lingering questions would be, why did the Malayalam-English baseline perform so much better? It had 84.3%. And another question is, why did synthetic data improve Spanglish while decreasing Malayalam-English performance in some cases? Right, so the first question we can answer by looking at the difficulty of the data set, because the Spanglish data has very ambiguous labeling because humans are inherently ambiguous people. And so, for example, the sentence "Happy Friday" was labeled as neutral by humans, but it was predicted as positive. And then a similar tweet that just says #Friday was labeled as positive, but predicted as neutral. And ultimately, the prediction, some people might agree more with the LLM prediction than the human label. Right, and the other thing is LLM-generated data generally has more accurate labels, so it can offset these challenges. Regarding the second question, this is all about how close the synthetic data can approximate the natural data. In Spanglish, we can see that both syntactically and semantically, the synthetic and natural data are very similar. They both use the same Spanish-English hybrid words like text they are, and they both generally contain the same amounts of each language. On the other hand, in Malayalam, there's often a lot of Malayalam in the natural data, whereas a lot of English in the synthetic data. And so this is just an example of how there's so many variants of code mixing. So even though the synthetic Malayalam sentences are labeled as natural by even humans, they're not as similar to the exact variant that's reflected in the test data that's from humans. And so this is just an idea that there's so many different variants and it's so hard to determine naturalness through just AI testing. Ultimately, LLMs still reflect an English-dominated world. Right, so in conclusion, this method, using LLMs to generate synthetic code mix data, improves code mix sentiment analysis by upwards of 10% in Spanglish. It's also 40 times cheaper than just doing human annotation, and is a really promising data augmentation method. It's most effective for resource-constrained situations, and specifically when languages are more evenly represented. And we also release the code, weights, and data on GitHub. Great. Thank you. Any questions? Yes.
So, for the presentation, you only use a few examples, very few, but there is like comparison if you put like more examples. So like why, is there a kind of rationale for the using 15 examples?
Yeah, so I tried 5, 15, 50, upwards of 100, and I found that from preliminary experimentation through fine-tuning that the 15 examples helped improve performance the most. And I would say this is because the LM context issue, once you give around like 50 shots, it becomes a huge amount of input, and LM tends to lose like the goal. And yeah, and I think in general works, at least for few shot prompting, most use under 20. Yeah.
In terms of next steps, what do you recommend? Because I know you said have a synthetic data set of English terms. I guess would you create a more I guess a realistic data set or something like that that would help the current models that are out perform better? I mean, cause I guess like you said with the synthetic data set, there was an improvement.
Yeah, right. So that's one major step. It would be integrating this like sentiment analysis model to actual like dialogue systems, actual conversation systems, so they can react to code switching better. Obviously, this would also entail testing on more languages, more dialects, because obviously there's many more out there with their own challenges. That's a significant direction. Another one would be expanding to speech, because code switching happens a lot of the times when you're talking, and it's very naturally occurring, and oftentimes when you're writing, it's less common for you to code switch, so that's a major direction. Any other questions?
This is like a deeper part of the question, but like when you collected the Spanish English data or like the Malayalam-English data, do you have ideas which countries or which regions those data came from? Because it could also be even for the same language, right? Based on the region that you're in, the proportions of the code mixed languages would tend to vary.
Right. Yes. So the specific data sets we use there from Twitter and YouTube, and so it's difficult to track the exact place. What I would say is there's common areas where these switches occur, specifically Spanish-English, often in Mexico and the California border, happens most frequently. And for Malayalam-English, mostly happens in India, so in areas of India. So I would say that, and I think you bring up a great point of different variants. It's funny because it's not just in different regions, but also even in, say, one household or one neighborhood. Because just to give an example, like when, because I code switch, I speak 3 languages, and depending on the person I'm with, I changed how much I use each language. For example, there's there's what's called matrix languages and embedded languages, and the matrix language is the language you're mainly using. The embedded language is you're inserting certain words in a different language. So say I would talk to someone in English and insert one Chinese word that's like a Chinese food. And it would depend on if I'm speaking to someone who mainly speaks Chinese and I insert some English, or I'm speaking mainly in English and inserting a little bit of Chinese. And so this just, it shows there's so much variability, and AI systems often desire rules, and it's difficult to actually define these rules.